His research interests are on making large-scale AI deployments more efficient and more sustainable. And he's on the job market this year, looking for other industries or postdoc positions.
Thank you so much, Christina. Hello, everyone. I'm Pratyush, and I'll be presenting our work on characterizing power management opportunities for large language models in the cloud. LLMs have exploded in popularity over the past year, with diverse applications spanning chatbots, search engines, code completion tools, and many more. To meet this growing demand, cloud companies across the board are spending billions of dollars into building new GPU clusters to run LLMs. However, a key challenge is that these GPU clusters draw a lot of power. The power usage of the typical server GPU has increased fourfold over the past 8 years, and it is likely to keep growing in future GPU generations. These trends have driven large-scale LLM deployments into a power wall. Power grids cannot keep up with the growing demand for LLMs, and data center construction timelines have already been pushed back by 2 to 6 years due to power supply shortages. Our work helps address this power wall for LLM deployments at scale. Specifically, we profile the power usage patterns of training and inference workloads in production clusters. We then analyze the design implications for managing power in large-scale cloud deployments. And finally, by leveraging our insights, we build a power oversubscription framework for cloud-based inference clusters. So let's get started by trying to understand the power usage patterns of these workloads. We'll look at training first. The graph here shows the power draw for fine-tuning an LLM on 8 GPUs. The data is normalized to the allocated power across all the GPUs, which is indicated by the dashed red line. The first thing we observe here is that the power draw often exceeds the allocated power. These peaks imply that unlike traditional CPUs, GPUs may need to provision an additional power buffer for safety. Next, we observe that training power usage is periodic. At the boundary of each iteration, the power drops by a lot and swings back up very quickly. These swings occur due to the computation and communication phases within training. The computation phases tend to draw more power, whereas the communication-intensive phases at the end of the iterations tend to draw much less. When we profile the power usage of training at scale, we find that these power swings are greatly amplified. The reason this happens is because training operates in a synchronized fashion across thousands of GPUs. As a result, the power usage peaks simultaneously across many servers, resulting in very little power headroom available in a training cluster. In contrast, let's look at what happens with LLM inference. When you query an LLM and get a response as a sequence of output tokens, there are actually two kinds of computational phases going on. The first phase is called the prompt phase, and it involves processing the entire input query to generate the first output token. Generating the rest of the tokens is a sequential process called the token phase, and that involves memory-intensive operations. Now, as you might expect, these phases also have distinct power usage patterns. The peaks here correspond to the prompt phases, whereas the troughs correspond to the token generation phases. At scale, we observe that unlike training clusters, inference clusters have a substantial headroom of nearly 20%. This happens because inference is not a synchronized workload like training. Instead, inference requests from a bunch of users are multiplexed on servers across the cluster. On average, most of the GPUs tend to be running the longer token draw phases, which brings down the overall utilization of the cluster. Next, let's take a look at how power management knobs impact these power draw patterns. GPUs offer a couple of different knobs for power management. The first is power capping, which lets us limit the power usage of the GPU to a configurable value. In LLM inference, since the prompt phases are power intensive, those are the ones that typically get capped due to power capping. The other knob that GPUs offer is called frequency scaling, and that lets us control the compute clock frequency of the GPU. Since frequency scaling slows down the computation in general, it impacts both the prompt and token phases and helps us reduce the overall power draw. Now, the trade-off with power throttling is typically that the performance gets impacted because you're no longer using the device to its maximum capacity. Here, I'll show a graph of how frequency scaling impacts the inference performance, and similar trends also hold for power capping. In general, we want to reduce the peak power as much as possible while retaining higher performance. So for reference, the dashed gray line indicates linear scaling. We find that as we reduce the frequency of the GPU, the data points tend to lie towards the top left of this reference line. What this means is that we can substantially reduce the power draw of inference with incurring very little performance impact, which is pretty good. And this data really makes a strong case to adopt GPU power management at scale, which is something that is not deployed in today's cloud-based LLM clusters. So given the promise of GPU-based power management, let's look at some of the challenges that come up when trying to design power management at scale. The approach that we'll look into is whether we can deploy additional servers under a given power budget. And in the remainder of the talk, I'll focus purely on inference because inference makes up most of the compute demand for LLMs as they grow more popular. You can find more details about training in the paper. So let's say we have this hypothetical inference cluster, which is provisioned according to today's methods, and that leads to underutilization like we saw before. Since we have this leeway, we could potentially deploy some more servers in this cluster, let's say 20 or 30% more. And this would be completely okay in the common case because most of the servers will be executing token phases. But in some corner cases, when, let's say, multiple prompt phases align together, it's possible that the power usage of the cluster might exceed the capacity that's allocated for it. And exceeding the power budget is really bad because it can cause power failures. To prevent power failures, we need to quickly reduce the cluster power usage to be within acceptable limits. Now, we could use the power throttling mechanisms that we just talked about for such kind of throttling. And since GPUs make up the majority of the server power usage in inference clusters, this would be a pretty promising thing to do. Unfortunately, in the cloud setting, these knobs are very slow. Throttling the GPUs on a single server takes nearly 40 seconds, and that is much longer than the 10 seconds that we have to shave off power usage in the cluster. So given that this is not going to ensure safety, what can we do? Luckily, there's another knob called the power break, which can be used to handle such situations. Power break is different than the GPU throttling knobs that we discussed so far, in that it's an extreme cluster level knob designed for power safety. The way it works is that whenever cluster power usage exceeds 100%, it kicks in and quickly throttles all of the servers in the cluster to a very low power usage. The downside is that it substantially also impacts the workload performance, which is something that we don't want. So we kind of have a problem. These GPU throttling knobs are nice, but they're very slow. And power break tends to cause very high performance overheads. So how can we reconcile this dilemma? In the remainder of the talk, I'll describe how we address this challenge and build a power over subscription framework for cloud-based inference clusters. Our framework is called Polka, and it manages GPU power to safely deploy more servers in inference clusters. Importantly, it does this in a way with minimal performance impact on latency-sensitive LLM inference workloads. Polka relies on two key inputs to manage power. The first is workload priorities, which help Polka capture the latency sensitivities of inference workloads. These priorities come up naturally in today's workloads. For example, an LLM that is used for search is probably much more latency sensitive than one that is used for document summarization. Similarly, paid services tend to be much more high priority than free services. The second input to Polka is the power usage traces in the cluster. This includes both the current power usage as well as the historical power usage traces. And these inputs help Polka infer workload variability as well as the power usage patterns. Together, Polka uses these inputs to configure its power management policy. I'll give you an intuition of how the power management policy works, but you can find more details about it in the paper. In general, Polka tries to be proactive in throttling power usage to ensure safety with the slow GPU power throttling interfaces that are available in the cloud today. In the worst case, if the cluster power usage reaches 100%, Polka relies on the power break to ensure safety. But to prevent the performance overheads associated with the power break, Polka proactively throttles workloads at lower thresholds in a priority-aware manner. For example, at the lowest threshold, Polka starts by capping only the low priority workloads. And if this isn't sufficient and the cluster power usage increases further, Polka caps both low priority and high priority workloads. The key idea is to really aggressively cap the low priority workloads to minimize the performance impact on the higher priority ones. By appropriately selecting these thresholds and actions, Polka ensures that it rarely incurs power breaks while preserving high priority workload performance. We evaluated Polka on power traces obtained from Microsoft's production clusters and replicated the power usage patterns using open source models. In our experiment, we simulate adding servers to an LLM inference cluster and evaluate the throughput and tail latency impact on low and high priority workloads. The input load is scaled proportional to the number of servers in the cluster. We find that although low priority workloads incur a high tail latency slowdown as shown on the right, they incur a fairly low throughput impact as shown on the left. In contrast, higher priority workloads tend to have negligible performance overheads due to Polka's priority-aware throttling mechanism. After adding about 35% more servers into the cluster, Polka starts to trigger power breaks to ensure power safety. Since we don't want a cluster that incurs power breaks often, it's better to be conservative and deploy slightly fewer servers in practice. If we deploy about 30% more servers, we can eliminate power breaks while still also having a very low performance impact on both low and high priority workloads. In this way, by adding more compute capacity under existing and upcoming clusters, Polka helps address the power wall for cloud-based LLM inference deployments. To summarize, we characterize the power usage of training and inference workloads in production clusters. We then analyze design implications for managing power in cloud-based deployments. And finally, we leverage our insights to propose Polka, a power subscription framework that deploys up to 30% more servers in existing and upcoming inference clusters. If you're interested in learning more, please check out the paper, which is linked there in the slides. And feel free to reach out with questions anytime. That brings me to the end of my talk. Thank you so much.
Hi, thanks for the talk. Very interesting. You mentioned there was a 20 or a 30-second lag on actually bringing power down. That's on the GPU side. Are you talking about the capping capabilities of like NVIDIA style devices? And yeah.
Yes. So there's about a 40-second lag that comes up. And this lag is for like out-of-band power management interfaces for the GPU. So if you're using an in-band knob like NVIDIA SMI, you can cap much quicker. But if you're trying to cap at scale, like you have a cluster manager, which is
okay. Oh, that makes sense.
Hi, I'm Bianchini from Meta. So you haven't talked about this in the talk, but I was looking at the paper where you mentioned changing the batch size could be another knob to reduce the power usage. And I was wondering which one is you think a better method in terms of the latency power trade-off?
Right. So in terms of the latency trade-off, like I think frequency capping tends to be better in terms of like just preserving performance. Changing batch sizes can have like more impacts in terms of like scheduling as well. And you need visibility into the scheduler to control batch sizes. So in a cloud setting, we can't really have that kind of a control if virtual machines are something that the provider is not directly controlling.
Got it. But if let's say you do have a control, it's not a cloud system.
Yeah. Oh, in that case, I think a combination of the two would be the preferable approach, because in some cases, like batch sizes can change your performance substantially. So depending on what is acceptable, you might want to pick and choose.
Got it. Thank you.
Thanks for the nice talk, Pratyush. I'm Deep. I have a question about where is Polka running? Is it at the rack level right now? And if it is rack level, have you considered the possibility that you actually have a power hierarchy? So you have racks, but then on top of racks, you have more switching breakers and so how would that work in a cluster where you not just have racks, but hierarchy of racks with different power buttons?
Oh, that's a great question. And it was a slide that I actually removed at the last moment, so I should have probably kept it in. So Polka is operating at the row level instead of the rack or the server level. And the reason we operate at the row level is because that lets us benefit from the statistical multiplexing of requests across servers. So inference requests will peak at the server level. So if you throttle based on that data, it is just going to be very aggressive in terms of power throttling. By monitoring at a higher level, it's just better to level out the power usage that you see at scale.
Hi, Matt Sinclair, Wisconsin. Really interesting talk. Nice work. Can you comment a bit more on the implications of, your claim, okay, we could put more GPUs, say, in the cluster. So with these large scale clusters that, compute centers or national labs or so on are using, they've kind of already sized it as if you're running all of them like at a given power level at a certain time. So, if we really added more GPUs, say, based on your study, wouldn't we then have to actually get like a bigger power line coming into the data center or into the compute center?
That I believe is not true, because essentially, like, once a data center is provisioned for, let's say, 10 megawatts, that 10 megawatt line is kind of expected, like the data center is kind of expected to consume that. And what we are saying here is that in practice, you're not actually consuming that much power capacity. You're actually underutilizing that. So how can you deploy servers in a way that you can actually end up using that power budget that you've allocated the data center for?
Maybe I'll talk with you later about it. I think we're passing each other. Okay.
Sounds good.
Thanks.
Thank you, again. All right, our second speaker is Walid. He's a student at Amherst, the College of Computer Science. His research focuses on sustainable computing and designing resource and energy efficient machine learning systems. And his work has been published in top-tier conferences, including ASPLOS'24 and Symmetrics. So he's not on the job market yet, but he's interested in collaborations and discussions on how to reduce the carbon footprint on computing.
Thank you, Christina. Hello, everyone. My name is Walid. So I'm here to present our latest paper, Going Green for Less Green, Optimizing the Cost of Reducing Cloud Carbon Emissions. So this work is done in collaboration with Qianlin, Noman, Abel, David, and Prashant. So data centers energy demand is on the rise. So there are some estimates that by 2030, 8% of global energy consumption will be from data centers. Even nowadays, there are some countries like Ireland where data centers consume around 14% of their country's energy demand. However, the issue is not really in the energy consumption, but also in the carbon footprint associated with energy consumption. So since most grids are powered by non-renewables, high energy consumption is often associated with high carbon emissions. One particular solution that a lot of people are thinking about is carbon-free electricity grids that might solve many of the sustainability problems. However, this is still a long-term solution, and even in the most optimistic forecasts are decades away. So the solutions that we and many other researchers are proposing is to directly minimize carbon footprint of computing through carbon-aware scheduling. So one particular way of minimizing the carbon emissions of computing through scheduling is to exploit carbon intensity variations. For instance, in a place like California, due to the high penetration of solar energy, carbon intensity is often lower at the day and higher throughout the night. So people start delaying their jobs from high carbon periods during the night to run more during the day. So in this case, there are some recent research work like Pratyush, Ecovisor, and Carbon Scaler that propose techniques and methods to minimize the carbon footprint of computing through temporal shifting. However, carbon-aware scheduling is not a free lunch, and it often comes with trade-offs never exploited in the earlier research. So one particular trade-off is the carbon and performance trade-off. So imagine a job that arrives at a high carbon period, and the user wants to minimize its carbon footprint. So the user will have to delay the job to a period where carbon intensity is lower. And the more the user is willing to delay the job, the more it can run at a more sustainable fashion. So this creates a carbon and performance trade-off where decreasing carbon emissions often increases waiting time and the decreasing performance. Another important trade-off is the carbon cost trade-off. So in this paper, we are considering batch workloads, and in a typical batch cluster, users create a reserved plus on-demand instance. The reserved instances cover the base demand, and on-demand instances are used to cover demand spikes. In this case, if you consider a carbon-aware scheduler to minimize the carbon emissions of your workloads, you will typically bundle all workloads at a low carbon periods. This will underutilize the reserved instances and maybe even leaving them idle. Idling them or decreasing the utilization will increase their effective price, and the increase of their effective price will increase the cost of your execution. So this highlights the carbon and cost trade-off that we are trying to that often happens with carbon-aware scheduling. So in this paper, we try to analyze the three-way trade-off of carbon performance and cost that happens in cloud-based batch schedulers. And we are trying to design carbon-aware scheduling policies and a carbon-aware scheduler to balance these trade-offs. So in this paper, we propose Gaia. Gaia is a carbon-aware scheduler that uses hybrid settings, so jobs can run on reserved, on-demand, and spot instances. And in this case, Gaia does not require changes in the job interface, where users, for instance, if they are using a Slurm cluster, they can submit the job the same way that they are usually doing. However, Gaia uses a carbon information service that presents current and future carbon intensity forecasts, and also it implements a detailed accounting of the cost and emissions of their execution. And when a job is assigned to Gaia, Gaia decides two things. Gaia decides when to run the job, the start time, and also decides where to run the job in terms of demand instances. So Gaia selects the start time and executes job to completion. And in Gaia, we propose three policies. The first policy is what we call the lowest slot policy. It selects the slowest slot within an allowed waiting time and start the job. And this policy does not consider the length of the job, so it might run the job just around very long jobs at the wrong time. To consider the effect of the length of the job, we consider the lowest window policy. We develop the lowest window policies that try to minimize carbon emissions by using cluster-wide statistics or cluster-wide information on the job length. So it uses, for instance, if I know the average job length, I can assume that this job, if I execute it around these periods, I will minimize the carbon emissions. Finally, we propose the carbon time policy that considers both the carbon efficiency as well as the performance overheads. In this case, I might not run at the greenest periods because the greenest period might be might introduce too much performance overhead for a minimal savings. Gaia policies also can be configured to be more conserving, where a variant that we call reserved first, or we use the spot instances, a variant that we call spot first. And please check the paper on more details on these policies. So in the experiments, we use three workload traces from the Alibaba, Azure, and Mustang HPC traces, and we also explore the trade-offs among different carbon intensity traces. For instance, we have six different carbon intensity traces that present different characteristics. For instance, a place like Sweden, carbon intensity is typically low and stable because it has a lot of hydroelectricity, while a place like California has a lot of solar energy. So it's more or less presents an average carbon intensity, but it presents higher variations. And finally, we deploy Gaia in two settings. We deploy Gaia in AWS parallel cluster to run week-long real experiments, and also we develop Gaia simulators to enable us to implement year-long simulations. And both of them are open source. So in the first experiment here, I'm going to show the carbon performance trade-off by using the week-long Alibaba trace using the carbon intensity traces from South Australia. In this case, we are configuring the maximum waiting time for short jobs to be 2 hours and for long jobs to be 24 hours. We differentiate between short and long jobs because this is typically what happens in an HPC, and where dealing short jobs a lot does not really is not really convenient, and also does not contribute much to carbon saving as we show in the paper. So in this case, we present three baselines. The first baseline is considered to be a carbon agnostic baseline, where jobs are executed as soon as they arrive. In this case, due to cloud elasticity, we can run the cluster at zero waiting time. Another baseline we are considering is a wait a while policy that considers tries to minimize the carbon footprint of workload by running in suspend and resume manner. And this policy assumes perfect knowledge of job depths. In this case, we minimize the carbon footprint by 40%, but at the same time, we run at the highest waiting time. In this experiment, it was around 9 hours. Another suspend and resume policy is the equalizer. In this case, it does not assume any job knowledge information. However, it still acts similarly to wait a while. It highly reduces carbon emission, but also it increases waiting time. The policies that we are proposing, typically we assume that our policies do not suspend and resume jobs and must run jobs to completion. In this case, the lowest window tries to minimize carbon emissions and minimizes carbon emission by 32%. And results in around 6.6 hours of delay. Finally, we show that our proposed carbon time policies that consider both the carbon reductions and performance results in similar carbon savings, but it can reduce waiting time by around 30%. So the key takeaway of this slide is that using first grain estimates can enable scheduler to achieve high carbon savings, and considering both carbon and performance can reduce by waiting time by 30% with similar carbon reduction to the state of the art. So another important trade-off is a carbon cost trade-offs. In the paper, we show that how reserved instances kind of dictate the carbon and cost trade-off. But in this case, we show that there are three operational regimes based on the amount of reserved instances that you allocate. In case you have, so in this shows that you can allocate an amount of reserved instance that can basically give you the whole carbon savings that you can get through the carbon aware scheduler, but also there are things where carbon and cost are really at conflict. And also we show that there is a phase where carbon emissions comes at a where increasing the amount of reserved instances increases both carbon and cost. So we experimentally show this trade-off, and for the sake of time, I will just go through them. And we show that there is actually a very visible carbon and cost trade-off, where increasing the number of reserved instances decreases the cost, and also it increases the carbon emissions. And for waiting time, because we are using a conserving policy, increasing the amount of reserved instances decreases the cost. So the reserved capacity sets the carbon and cost trade-off, and utilizing the right amount of reserved instances balances the carbon and cost. We also implement large-scale experiments. I will just go through them a little bit quicker. We show that using year-long simulations, the trade-offs still present themselves. And we show that how different policies, for instance, if I have a cost-aware policy, it kind of runs at the highest carbon, and the other way around. If I'm using the carbon-aware policy, it runs at the highest cost. And however, we show that our policy can achieve some carbon savings for a minimal cost overhead. And we also show how different trace characteristics affect this carbon and cost trade-off. So in this paper, we introduce a carbon performance and cost trade-offs of carbon-aware scheduling, and we have shown the effects of these trade-offs in multiple settings. We introduced Gaia, the carbon-aware scheduler for cloud-based HPCs, and that utilizes realistic cluster information and settings. Finally, we listed some insights on how to balance this inevitable trade-off between carbon performance and cost. Thank you. If you have any question, I'm happy to answer them.
Nice talk, thank you. My question is about fairness. Does your scheduling algorithm has any implications on fairness based on the job duration?
So the only differentiation that we have now is that we differentiate between very small jobs around like less than 2 hours and like long jobs that are a little bit longer. But we do not have an explicit fairness criteria in this case.
Thanks.
Matt Sinclair, Wisconsin, really interesting talk. I'm curious how users view this. In my experience with sustainability, metrics, users have almost no visibility into saying like when I'm willing to run my job or how long I'm willing to wait or anything like that. And you have some sort of metrics that you're using here. So I'm curious how you implemented that or how you view it as being used by the wider public in the future.
Okay, so so in the recent years, there is a lot of visibility in the carbon electricity of different grids. So we typically rely on services like electricity maps and what time to give us around real-time carbon intensity. And by mapping these locations to this carbon intensity, to map the location of the data center that we were using to a carbon intensity trace, we kind of assume that this is the electricity, the electricity carbon footprint the layer is currently subjected to. However, I know that cloud providers have different accounting methods, but we are not really addressing this right now.
Sorry, just to clarify, I was asking how a user would interact with this, right? Like, how would a user say, I'm willing to wait longer to use a more green, energy source for their job?
So, for instance, if you are running in a data center in Virginia or in data center in California, you can go to the Kaiser electricity website and see the current or use any service that gives you the carbon intensity directly and assume that this is the electricity that you are running from. However, cloud provider currently do not give you the API directly for the user to use.
Yeah,
I hope this answers the question.
Yeah, that's the problem.
Yes.
Exactly.
Hi, I'm Isha Choukse from Microsoft Azure Research. Great talk. My question was, regarding the carbon cost points that you made, right? So you are looking into moving the VM from one region to another based on...
In this paper, we're mostly focusing on spatial shifting, but temporal shifting is definitely on the horizon.
Got it. And did you look at how the availability of the cluster could be impacted just based on, moving the workload over time?
So in this paper, we are using the user perspective, where the cloud is an infinite amount of resources that I can use in a way that I can use. But definitely, we are considering more in our current work, we are actually building these kind of algorithms while assuming cluster limitations.
Sounds good. Thank you.
Okay.
Our third speaker is Professor Liang. We couldn't make it in person, but we have a recorded video of the talk. He's a full professor at Ghent University in Belgium in the Department of Electronics and Information Systems. He also got his PhD from Ghent University in 2002. And his research interests include computer architecture, especially performance evaluation and modeling, workload characterization, dynamic resource management, CPU, GPU microarchitecture, and sustainability. And he has won a lot of his paper awards, and he's a fellow of the Goiri and the Institute.
I'm happy to present Google, a first order volume model to assess processor sustainability. Unfortunately, I couldn't make it to San Diego because I fell sick last week and I couldn't travel over the weekend. So global warming is a significant issue as a result of greenhouse gas emissions. And ICT is actually responsible for 2 to 4% of global greenhouse gas emissions, and it's rising. And this is on par with the aviation industry, so we really have to act. If you look at the carbon footprint of a computing web, it really consists of two parts. There is the memory footprint and there's the operational footprint. And the memory footprint can be further split up in upstream memory footprint because of manufacturing, and then downstream memory footprint because of recycling. And in the middle, we have the operational footprint because of product use during the lifetime of the device. There is massive inherent data uncertainty because of unknowns and secrecy. Regarding raw material supply chain, semiconductor manufacturing, for example, yields, expected lifetime energy mix, intensity of use, etc. For example, this iPhone LCA life cycle assessment reports recognizes that there is data uncertainty and that Apple is using, for example, industry averages and assumptions if some of the data is unknown to them. When it comes to product use, there's even more uncertainty when we rely on historical data of similar products. To make things even worse, there's a rebound effect, and it's actually quite counterintuitive, I'm sorry, making an individual device more power efficient actually leads to an overall increase in energy consumption. And this is also known as Jevons paradox, and it goes back to the coal-fired steam engines, which were made more efficient, but which led to an overall increase in the consumption of coal. So how to reason about sustainability in the context of computer architecture while there is so much massive inherent uncertainty? I take on it is to actually embrace it. And this is where Focal comes in. So Focal is a first-order carbon model. It's a top-down characterizing model that is deliberately simple, both upon first principles and it provides insight. And the key idea is to use proxies for the embodied and operational footprint, and these proxies are chosen such that the computer architecture can actually reason about those. And then we parameterize the relative importance of the embodied versus the operational footprint while considering different use cases, and including rebound effect. So despite Focal being so simple, it actually allows for reaching very powerful conclusions and with respect to the inherent data uncertainty. So if you reach similar conclusions across a range of scenarios and across the different confidence bounds, we can actually be more confident about our conclusions. So what is the proxy for embodied footprint? We all know that a wafer is a production unit in a semiconductor fab. And so the bigger the size of a chip, the higher its embodied footprint is going to be. So this curve is showing the normalized embodied footprint per chip as a function of die size, accounting for the lost silicon wafer area around the edges and accounting for yield. It's clear that proxy for the embodied footprint could be chip area. What is a proxy for the operational footprint? While we consider two scenarios, a fixed work scenario, where the amount of work that is being done is fixed over its entire lifetime. In that case, the operational footprint is obviously correlated with energy consumption. So the proxy here is going to be energy consumption. The second scenario that we're considering is a fixed time scenario. It's probably a more realistic scenario. And so here, the amount of work that we do increases. And so we assume here that the data that the device is using is the same amount of time. So in that case, the operation footprint becomes proportional to power consumption, as you can see in the little illustration at the bottom right. So the proxy here is power consumption. So how to weigh the embodied versus the operational footprint? Well, this ratio is really depending on a number of factors. And the first one is device type. As put that all figured out. Battery operated devices are mostly dominated by the embodied footprint, whereas always on devices are mostly dominated by the operational footprint. The ratio also depends on the lifetime of the device. And it also depends on the energy mix of the device. So the solution here is to actually parameterize the embodied versus the operational footprint in the form. And so Focal could reduce to what we call the normalized carbon footprint, or NCF, for the two scenarios, fixed work and a fixed time scenario. And it's really the sum of a weighted normalized embodied footprint using the area proxy, plus the weighted normalized operational footprint using the energy and power in case of the fixed work and the fixed time scenarios. And then further, we have the output parameter to relatively weigh the embodied versus the operational footprint. So as the second part of the paper, I'm using Focal to evaluate the number of archetypal processor design choices, and I've been classifying them into either strongly sustainable, weakly sustainable, or not sustainable. So strongly sustainable means that it reduces the carbon footprint and the fixed work and the fixed time scenario. So it's actually quite robust, and there's no risk for a rebound effect. Weakly sustainable means that it reduces the carbon footprint only for a fixed work scenario and not a fixed time scenario. So there's actually a risk, significant risk for a rebound effect. And then there's less sustainable if the design choice leads to an increase in carbon footprint under both fixed work and the fixed time scenarios. So I've been evaluating a range of processor design choices and I've been classifying them into these three categories. And all these results in the papers were obtained using algorithm models and previously published results. So the carbon footprint of this research work is actually quite low, except for me drinking coffee while doing research. So I'm going to give you just a few examples that shown in the paper. The first example is multi-core. So multi-core is actually strongly sustainable compared to single core. As you can see in the line one, which shows normalized carbon footprint as a function of performance. The black curve is showing single core processors, and the colored curves are showing multi-core with different degrees of parallelism. So it's clear that multi-core always reduces the normalized carbon footprint, and if parallelism is high, you can even achieve higher performance. Second, our writing software is weakly sustainable on the left-hand side, which is the fixed work scenario. We actually see a decrease in normalized carbon footprint as we increase the degree of parallelism, whereas on the right-hand side, we see an increase in normalized carbon footprint as we increase the degree of parallelism. So writing software is weakly sustainable. Our writing software is also more sustainable than adding cores. Look at the design points here. So this is a 32-core system versus a 16-core system, and the 32-core system has a level of parallelism of 0.9, whereas the 16-core system has a degree of parallelism of 0.95. So increasing parallelism is a more sustainable way than increasing the number of cores. Second example is CPU speculation. I'm using branch prediction here as an example where you're comparing a large hybrid line predictor versus a small memory predictor. So the large hybrid predictor increases performance by 14%, but also reducing energy consumption by 7%. As a result, we end up with a higher 6.6 higher power consumption. The figure on the right-hand side shows the case where alpha equals 0.2. Here we can see that branch prediction is actually really sustainable. Under a fixed work scenario, we reduce total carbon footprint, whereas under a fixed time scenario, we actually increase the carbon footprint. When the embodied footprint dominates on the left-hand side, alpha equals 0.8, we can see the branch predictor actually leads to an increase in normalized carbon footprint. So the branch prediction in that case is not sustainable. Third example is dark silicon. Dark silicon fundamentally trades off chip area for power efficiency, and this leads to an increased embodied footprint and a decreased operational footprint. So the question is, does this lead to an increase or decrease in footprint? So here we're assuming that an accelerator consumes about 500 times less energy for similar performance while taking up 2/3 of the total chip area. So when the embodied emissions are dominating, dark silicon is actually harmful in terms of sustainability because the total carbon footprint is much higher compared to general purpose computing solution only. And when the operational emissions are dominating, you need to use dark silicon very frequently, which obviously isn't possible. So the overall conclusion is dark silicon is not sustainable. So with these insights, I try to understand or pave the way for designing sustainable multi-cores across frameworks. So the baseline here is a processor in the current tech node, and the question is how many cores should be provisioned in the next generation tech node? So if you go for 4, 5, or 6 cores, you actually end up with a strongly sustainable solution because this leads to lower carbon footprint, and at the same time, we get a significant performance boost, as you can see in these two graphs. Whereas with 7 or 8 cores, you end up with a weaker or less sustainable design choice. So there is a risk of an increased footprint using all the available transistors. So the bottom line is here that we can actually use the increase in available transistor count in a solar way, and by doing so, we can actually reduce the total carbon footprint of processor design moving forward. And this is in contrast with what industry is doing these days. So to that, sustainability is a grand challenge. Poker is a first-order parameterized model, and it allows you to investigate the sustainability impact of processor design choices. Thank you for your attention.
It's not, it's not in?
It's not.
Okay. Then.
Are we expecting to go? Maybe you can offline. Our next speaker is Ricardo. He's a systems researcher at Microsoft, focused on high-performance computing and machine intelligence applications. Before joining Microsoft, Ricardo was a senior silicon design researcher at AMD Research, and his primary research field there was computer architecture. He earned his bachelor's degree from BITS in Planning Media and his master's and PhD from Georgia.
Thank you so much. All right. Hi, I'm Srikanth and I'm going to talk about our work, which is titled Predict, Don't React for Enabling Efficient Fine-Grained DVFS in GPUs. The insight behind dynamic voltage frequency scaling, or DVFS, was that workloads exhibit phasic behavior, and if you can dynamically tune your voltage and frequency, you can build really power-efficient architectures if managed properly. But with the advances in technology, there is a need to rethink the designs that we did for DVFS, specifically for this fine-grained DVFS in GPUs. So let's look at that. So on one hand, we have advances in power and clock delivery, like IVRs and FLLs, which enable these fine-grained, fast transitioning dynamic clock domains, which can transition every few nanoseconds. So you can change your voltage and frequency in a matter of few nanoseconds. So you can change your voltage and frequency every microsecond without any overhead. So it gives us a lot of advantage in terms of power efficiency. On the other hand, we have GPUs, which with their higher power limits and wider dynamic voltage ranges, which have the potential for power savings, and you can utilize these technological advances, but they have a complex execution hierarchy. They are composed of wavefronts and warps or thread blocks and CDAs, and these thousands of threads make it really harder to predict the behavior of these workloads. So if you look at the current state-of-the-art DVFS control mechanisms, they are reactive in their approach, which means that, let's say you have been executing your workload and you have just executed one time epoch, you can extract the performance counters and estimate what your phase was, or in other words, were you compute intensive or memory intensive. You figure out what your phase was and then apply an optimal voltage and frequency for the next time epoch. What you're doing here is basically assuming that if you were compute intensive for the last time epoch, you are probably going to be doing that in the next time epoch as well. What we are suggesting today is a new kind of mechanism called predictive mechanisms, which not only looks at the last time epoch that you just executed, but a set of time epochs from the previous, from your past. So in this talk, I'm going to outline some of the challenges in enabling such fine-grained DVFS in GPUs. Then I'll talk about a new metric that we define, which is called frequency sensitivity, which actually helps us in designing better predictive DVFS mechanisms. I'll talk about how we can take previous works on CPUs and apply it on GPUs and what are the challenges involved in that. Then I'll talk about the heterogeneous nature of the GPU workloads itself, which makes this predictive designs a necessity. And finally, I'll talk about our design, which is called PC stall. It's a PC-based, program counter-based, wavefront level sensitivity predictor. And finally, I'll talk about our results. We evaluate our design across a diverse set of GPU workloads, both high-performance computing and ML workloads. So let's look at the state-of-the-art DVFS techniques, which we define involves estimation and reaction. So the high-level objective is I want to select the optimal voltage and frequency for a time epoch according to its phase, or in other words, frequency sensitivity of the work being done in that time epoch. So let's say you have been executing your workload, you just executed one time epoch at frequency 2, and you got some work done. So now your first job is to figure out what its phase was. Or in other words, what could have been the work done if you had executed the same time epoch in another frequency. This is what we call estimation, where you're estimating what your phase was. The next step in state-of-the-art techniques is to react to this time epoch that you just execute it. So you take the information that you got out of the time epoch and figure out that maybe I should have been executing it at frequency 1. So you set your frequency and voltage for frequency 1 and execute your time epoch. And after you execute your next time epoch, you repeat this process. So in general, there are three challenges here. One, what is a good metric for classification of a phase? What makes a time epoch compute intensive or memory intensive? Challenge number two, how do I estimate it during runtime on the hardware of an executed epoch? So I just executed an epoch, but how do I figure this out and what it would look like? It would have looked like if I executed an another time epoch. And challenge number three, with all this information about past time epochs, how do I estimate the optimal voltage frequency setting for my future time epoch? And these are the three challenges that I'm going to talk about. So challenge number one, what is a good metric? We figured out this metric, which we define it as delta instructions committed in the clock domain divided by the delta in frequency, which is how many more instructions are you committing when you go from, let's say, 1 gigahertz to 2 gigahertz. If you're committing more instructions, you are probably compute intensive, and if you're committing less instructions, you are probably memory bound. And we ran this metric through our diverse set of workflows and figured out that this metric is linear enough and works out well for the kind of work that we're trying to do here. Challenge number two. Whoops. Sorry. Okay. No, it's flickering for some reason. All right, sorry about that. So challenge number two, how do I use those estimation models that have been developed for CPUs about a couple of decades ago for GPUs? So the state-of-the-art way of doing this is to take this estimation models and apply it on CU level or SM level estimation. But what we see is that warps or wavefronts are more akin to the thread-like independent progress that CPU threads had. So take those estimation models that we developed for CPU threads and apply it on wavefronts, not SMs or CPUs. This helps in actually parallelly and analogously apply those estimation models on GPUs. And now challenge number three, I have all the information about the past time epochs. How do I apply for my future time epochs? Now the state-of-the-art technique was to be reactive, which is take information from the last time epoch that you just executed and use it for the next time epoch. We measured that on our GPU workloads, and what we see is that if you do that, on an average, you are 37% different than the last time epoch, which means if you take the optimal voltage frequency for your last time epoch and apply it on to your next time epoch, you are wrong 37% of your time. So why is that in GPUs, especially at these fine-grained time scales? So we decided to look a bit deeper into that. And what we figured out is that at these smaller time scales, you are probably executing a different set of instructions than what you did in your last time epoch. So take this example of this code piece that I'm showing you here. Epoch 0, let's say it was compute intensive, you just executed it. Epoch 1 could be a memory intensive workload. Now you're doing the next iteration in your GPU code and you land it at the beginning of Epoch 2. Now reactive models would look at Epoch 1 and take the information from there, but the smarter thing would be to look back in time and see when was the last time I executed a similar piece of code, and that would be Epoch 0. So ideally, what I would want to do is that not to look at the last time it worked, but the last time I executed a similar piece of code. So we take this insight and try to measure it on our workloads, and basically looking at when was the last time I executed a similar piece of code. And we do that by using the program counter of the epoch that I'm just about to execute. What we see is that when we measure the change in sensitivity from the last time I executed a similar piece of code, that difference is just 11% compared to the 37% I was observing when I was measuring the change in sensitivity across consecutive time epochs. So we take this insight and build a design which we call PC stall, a PC index sensitivity table using the stall estimation mechanism. This system is simple. There are two procedures. One is called lookup, which is about the epoch that we just executed. One about the epoch that you're about to execute, and update is for the epoch that you just executed. So let's say you just executed one time epoch, you would collect all the performance counter data and send it to this table. Where it will estimate the sensitivity using that data and store it in a PC index table. And for the next time epoch that you're just about to execute, you use your current PC to index into this table, retrieve the sensitivity from probably the last time you observed a similar PC address, and sum over these sensitivities for all the waveforms that you have in your clock domain. So if you have, let's say, multiple waveforms in your clock domain, you just add the sensitivities up. And the linearity of the metric that we just introduced in challenge 1 allows us to do this. This also helps us in estimating the sensitivity inherent to the parallelism of GPUs. So what does all of this buy us? What this buys us is improvement in prediction accuracy of my optimal voltage and frequency setting. So what I'm showing you here in red bar is CRISP, the state-of-the-art model. And you can see that it only reaches up to 60% accuracy in these fine-grained timescales of 1 microsecond. With the best reactive models and with the best information that I could have, but only looking at the past time epoch, I could only reach 63% accuracy. But with our design, PC stall, it gives us a step function improvement over these accuracies, delivering about 82% accuracy. And with improvements in the estimation model, it can go up to 90% of the overall accuracy compared to an oracular prediction mechanism. So what does it mean in terms of power and energy efficiency? What I'm showing you here is the energy delay squared product. So lower the better. PC stall delivers up to about 48% of oracular savings compared to the 23% provided by a state-of-the-art technique normalized to static execution. So as you can see, PC stall is pretty close to my oracular execution and delivers most of the benefit that I could get out of this. So in summary, the takeaways are that, when you have shorter time epochs, there is a need to redesign your DVFS control mechanisms. And in general, if you have heterogeneous behavior, it could lead to inefficient voltage frequency selection. And if you're taking CPU estimation models and applying it to GPUs, apply it at a wavefront or a warp level, not at an SM or CU level. And finally, if you're trying to predict the performance of GPU, don't just look at the last time epoch, but look at the last time you executed a similar piece of code. And in that direction, we propose PC stall, which is a PC-based, program counter-based indexing table, and that delivers us 81% accuracy and 48% improvement in energy delay squared product. Thank you so much.
Yeah, I'm Leonardo Pica. I'm in Meta. So it seems like that you are doing decisions at 1 millisecond or microseconds. And usually in the real hardware, this is done by a microcontroller running a firmware that usually cannot do these decisions at this fast time granularity. So what is the minimum level that you can do? Like, for example, is a millisecond decision good enough, or do you need the microsecond scale? Thank you.
Yeah, that's a great question. So, currently, these DFS control decisions are made by firmware working on a microcontroller. But with the advances in technology that I'm talking about, IVRs and FLLs, these kind of decisions can be made on the hardware closer to the core, and you can make these fine-grained voltage and frequency selections during execution. So you're making these decisions pretty close to the actual clock domain, and these changes are only enabled because of these advances in technology. So in the paper and in the first slide, I actually present what the improvement could be with smaller and smaller time scales. And what we see here is basically with finer grained time scales, you get more power efficient architectures, and you will be able to save as much power as possible. Thank you so much.
I have a lot of questions, but I only have one here and the rest for the coffee break. So my question is actually for if you go towards the other direction, where instead of running this within the GPU firmware, how would you think it would make sense if we put it in the user space as a policy that executes on a much coarser granularity? And the reason why I'm asking is, if I want to do this for NVIDIA GPUs, I don't have access to the NVIDIA firmware. I can't modify it, but I can modify it based on some sensors at the OS level. Would this still make sense, or do you think that's too coarse-grained?
Yeah, I think if you're looking at these fine-grained timescales, it's the hardware that's supposed to make these decisions. If software tries to make these decisions, you would spend a lot of time just going to the memory and back to actually fetch the right optimal voltage frequency setting or your code that you're probably going to run. So if you're going to such timescales, it's preferable to do this at hardware. But these companies like AMD and NVIDIA could provide us as users APIs to do these and to enable such functions, maybe inserting compiler hints into the code, and which could eventually be taken in by those hardware units that are present inside the hardware and making these decisions much more easier. But in general, exposing these complete DFS control to software wouldn't make sense when we're working at these small time scales. Thank you.
Hi. So it seems like the fine-grained control is in the time scale level, but my question is do you have fine-grained control in the spatial domain, like in terms of cores? I mean, I think NVIDIA GPUs only have like 1 voltage domain per chip per GPU. So I was wondering, if you do have that in this work here, or based on the application characteristics you have seen, do we need for more finer-grained control per SM or?
Yeah, that's a pretty great question. And yes, so we did analyze that in the paper, going from a clock domain just for one CU or SM to multiple CUs to the whole GPU. And obviously, you'll get more benefits if you have fine-grained clock domains spatially, but then there's also an overhead of having such tables and voltage regulators and frequency providers at these fine-grained timescales. Obviously, with this chiplet era where we are having chiplet-based GPUs, we could and we probably need to have separate voltage frequency domains even within a single GPU. So we are probably going to see more and more of that in the upcoming generations of GPUs from both NVIDIA and AMD. And that this is kind of a design which would be really useful in that scenario where you have these spatially small fine-grained timescales. But the paper has all these results.
Okay, got it. Thanks.
Thank you so much.
All right, in our final talk, we have 2 presenters, Donald Jupiter and Stefan Kapis. Donald is a PhD student from the Graz University of Technology. In his work, he focuses on microarchitectural side-channel attacks and raw hammer. And his work has been presented at several security conferences, including IEEE security and privacy and music security. It will be on the job market in about a year when he's done with his PhD. And Stefan got his master's degree in computer science from North Carolina State University last December, and he's currently a software engineer at Google Cloud.
It's working before.
Yep.
Maybe try just HTML.
Can you try HTML directly?
Cool. Try without the adapter.
Yeah. This one's working, yeah.
Start the presentation.
Wonderful. Thank you for the introduction. I'm Jonas and I'm presenting today with step one.
Yep. So everyone knows what overclocking is, but what is undervolting? Undervolting is a similar technique used where instead of increasing the frequency while keeping the same voltage, we drop voltage while keeping the same frequency. This can lead to better power consumption and sometimes even increased performance.
How can it increase performance?
Here's the fun fact. If you usually, when we run our CPUs, we are limiting our performance by either the thermal limit or a power cap. When we lower the voltage, we actually have a bit more room to increase the frequency while staying at the same thermal or power limit. And if you look at this table, we have some measurements, and we can clearly see that while undervolting by 97 millivolts, we can reach 16% less power consumption with increase in frequency of 3.3%, leading to 23% improvements in the efficiency. But if it's so good, why don't we use it all the time?
Yeah, there's some problems with that because undervolting can cause reliability issues. So if you do it too much, your CPU can just hang. That's not nice. And even worse, it can cause security issues. And we don't want that. But why does it cause security issues? Let's talk about faulting instructions for a second. So our work found that some CPU instructions require a higher voltage to run than most parts of the CPU. And there are some CPUs out there where, for example, the integer multiplication instruction requires 150 millivolts more than the most part of the CPU. So the CPU keeps running, but Íñigo starts to produce faulty results. And this is a table from also prior work where they analyzed all the instructions that fault when undervolting a CPU, while the CPU keeps running normally. And these faults are undetectable, and that's a problem.
But what's so special about Íñigo in this case?
Oh, yeah. So we have a lot of vector instructions there and Íñigo. And Íñigo is special because it's used a lot. We do integer multiplications all the time. If you, for example, think about array lookups, you always have to multiply with the data type size of the array, for example. So there are a lot of multiplications and it's highly optimized and therefore it requires just a higher power budget and a higher voltage than most other instructions. And there were some exploits built with undervolting. They attacked trust zone with overclocking, trust zone with undervolting, and also Intel-SGX with undervolting. So these instruction faults are real and they can be used to exploit systems.
But we could save so much power if we undervolt our computers. What if we just straight up disable the instructions that could be potentially faulting? I mean, there are some questions like, is it going to be worth it? Will we even get enough energy savings to justify it? And will the CPU still be secure if we do it?
Yes, yes, and yes, we can do that. And this is how we do it. So we propose this hardware design to do that. And we start with MSR, where the operating system can disable specific opcodes. And then whenever the CPU executes an instruction stream, it checks if an opcode is disabled. And if this is the case, or if it's not disabled, it of course executes the instruction. If it is disabled, it raises an exception to the operating system.
And like with any other exception, we need a handler for that. So we provide a handler in the operating system for that hardware exception. And in this exception handler, we are going to be talking to an operating strategy that we can define for this specific instruction. And one way to handle a disabled instruction is to straight up emulate it without running it on the CPU. And we discussed this option in the paper in more detail. And now we're going to focus on the other option, which is switching DVFS curves. So if we're running at an efficient undervolted DVFS curve, we can react quickly to the potentially disabled instruction, use a new control MSRs that we're introducing into the CPU to adjust the DVFS, and enable the offending instruction, letting it execute normally.
So this is how this looks like. We propose that a CPU comes with two DVFS curves. Current CPUs have a single one that we show here as the conservative one. And usually our CPU now is running on the efficient curve with these instructions disabled. And now if one of these instructions is about to execute it, we have two options to go to the conservative curve. The first option is to just increase the voltage. So first we undervolted, now we increase it. The problem is that this takes quite long. The other option is to decrease the frequency.
decreasing the frequency is fast, but now the CPU is running at the lower frequency. So we lose some performance there, and that's not nice.
Yeah, so we have these two options, and in our operating strategy that we're proposing, we're actually going to combine these two. So let's look at an example of how this would work on a real workload. So imagine that we're running at an efficient level, so we have high frequency and low voltage. And now we encounter a potentially faultable instruction that is disabled. In this case, our operating strategy will quickly react by decreasing the frequency to go back to the conservative curve so that executing the instruction is safe. And we can start executing these instructions, not hitting the disabled MSR. But after some time, we still want to get all of the performance that we had before. So the next step our strategy will take is increase both the frequency and the voltage, just like modern CPUs move along the conservative curve all the way. And after we're done with the burst of these potentially faultable instructions, we can lower the voltage back down to return to our efficient state, which is now our status quo, and we continue our execution as normal.
There's one thing left. We talked about IMUL at the beginning, that it's so highly optimized because it's executed so often. If you would trap every IMUL execution with an exception and then go to the operating system and change curves, this would basically stop the CPU from working because we do that so often. So what we do for IMUL is we increase the latency by 1 clock cycle. Currently on CPUs, it takes 3 clock cycles to execute one integer multiplication. By increasing this clock cycle to 4 this latency to 4 clock cycles, we just have to do less work in 1 clock cycle, and this reduces the voltage requirements of integer multiplication. And we also evaluated the performance overhead of that.
Speaking about evaluation, how do we evaluate this kind of design? It's not like we have access to an Intel Foundry at this point.
Yes, that's a problem. So of course we could not really try this in hardware because we cannot build this hardware. What we did is we tried to do as much hardware measurements as possible. So for example, we measured how long it actually takes on the Intel CPU to change the voltage. So we wrote kernel modules for that. We changed the voltage, and then we measure how long it takes for it to actually change. We also measured how long it takes to change the frequency. For example, what we see here, voltage takes around 350 microseconds. Frequency is done in around 22 microseconds on modern Intel CPUs. So frequency is a lot faster than voltage. Then this table we saw at the beginning. So we undervolted CPUs. We ran spec CPU 17 benchmarks and actually measured the performance impact, but also the efficiency impact on these CPUs, Intel and AMD. This works on both systems. And we also measured the impact of the latency increase of IMUL. For this, we used Jump5 because this is nothing we can do in real hardware. And what's really interesting here, the mean over all spec CPU benchmarks is negligible. So it's 0.03%. So this is not really there. And what we see here, there's no linearity in the lower latencies. And we think that out of order execution actually hides this latency increase in most cases. And there's only this one outlier, the X264 video encoding benchmarks. It performs a lot of integer multiplications, and therefore out of order execution is not enough to hide the latency increase.
So now that we have the data for our CPU simulation, what do we do about the workloads? In order to run our simulations properly, we collect detailed instruction traces telling us where exactly in a real workloads program execution we encounter these potentially faultable instructions. And on the graph here, you can see the low points are small clusters of faultable instructions being executed in quick succession. And the larger gaps with the higher line above them indicates large gaps between these instructions where we do not encounter any of them. So now that we have these traces and we have all of the hardware data measurements, we can perform a proper simulation of what a workload running on our proposed CPU will be. And here are the results.
Yeah, so we did this for all spec CPU benchmarks. We also ran Nginx and VLC to have some more network benchmarks. So VLC was streaming a video there. And so we tried 2 different undervolting offsets of -70 millivolts and -97 millivolts. And we see that with -97 millivolt offset, we get an 11% increase in CPU efficiency with a slight increase in performance. If we only undervolt by 17 millivolts, we still have a 5% efficiency gain and a slight performance decrease of less than 1%. And we have a lot more results in the paper if you're interested in that. So we tried it on many different CPUs, different strategies, stuff like that. I want to highlight one result here. These are our best results. If we disable most of the faulty instructions at compile time, so we compile the spec CPU suite without using vector instructions, we see basically no curve switches and no exceptions. And with this, we are able to gain over 20% in efficiency.
So to get to our final remarks, undervolting can indeed be made secure. And if you want to learn more about such things as analyzing the aging and temperature guard bands that we are also maybe eating into, if you're interested in exception delay measurement for hardware exceptions, emulating the faulting instructions as we mentioned before, compiling without faulting instruction altogether, see the results above, or the detailed security analysis, please go and read the paper. Thank you so much.
Thank you.
Hi, my name is Armand. I'm from the University of Michigan. I love the talk format. The question I had, maybe I missed it, is how does undervolting help increase the performance? Is it like a heat thing or?
Yes, it is mostly the thermal limit and the power caps that may be introduced in the firmware level. So if we use lower voltage, it means that we use less power to perform the same operations. So we can slightly increase the frequency before we hit that limit.
Got it. Thank you so much.
Hey, good talk. I'm Ian from UW-Madison. With optimizing around specific types of instructions, is this technique ISA independent, or are there concerns with implementing this for arbitrary ISAs?
So these exploits that use these effects, they were shown on ARM and Intel CPUs. So yeah.
Okay.
It is independent.
Thank you.
Last questions?
Hey, so usually these curves, it's derived at the foundry during the beginning part. So how do you envision to derive the two curves? Do you have to have a set of workloads that don't use instructions? Like, what are your thoughts to derive the two curves?
So we propose that both curves are defined by the manufacturer at the foundry, because the manufacturer has insight on how the instructions work and yeah, maybe executes workloads without using these instructions to derive both curves.
Good, let's thank the speakers.
And try the bridge.